Our next illustrated example features a household known to consume 24 kilowatt hours of energy a day on average. Let's say the owner is considering investing in a PV system. Let's say the house is located in a relatively sunny area of the country and regularly experiences peak sun for the following lengths of time, depending upon mounting configuration of the modules, of which there exist three options. First, a fixed tilt stationary mount on the roof, which regularly experiences 6 hours of peak sun. Second, a single axis tracker, a device that follows either the sun's elevation or orientation but not both through the sky, which regularly experiences 8 hours of peak sun. And finally, a dual axis tracker, a device that follows both the elevation and orientation of the sun through the sky, which regularly experiences 8.5 hours of peak sun. See if you can determine the power rating of the solar array necessary to produce the desired 24 kilowatt hours of energy daily, given these different mounting configurations. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. If energy is power times time, power is energy over time. Let's first examine the fixed stationary mount. 24 kilowatt hours over 6 hours demonstrates a 4,000 watt or 4 kilowatt solar array would provide the desired power rating. Let's now examine the single axis tracker. 24 kilowatt hours over 8 hours demonstrates a 3,000 watt or 3 kilowatt solar array would provide the desired power rating. Finally, let's examine the dual axis tracker. 24 kilowatt hours over 8.5 hours demonstrates a 2,823.5 watt or roughly 2.8 kilowatt solar array would provide the desired power rating. Notice how the fixed stationary mount necessitated a larger array to extract the desired 24 kilowatt hours of energy each day than did the dual axis tracker. This makes perfect sense. The dual axis tracker works longer given it's capable of following the sun's orientation and elevation through a larger portion of the sky, whereas the fixed roof-mounted array only directly experiences a portion of the sun's path. Before we move on, allow me to comment briefly about the term peak sun hours and variable power output. Consider the fixed tilt stationary mount, which regularly experiences 6 hours of peak sun. This most assuredly does not mean that the sun immediately rises and shines at full intensity for 6 hours and then immediately sets and plunges the world into darkness, but rather the sun shines with varying intensity for varying periods with varying cloud cover such that it ultimately produces an equivalent amount of energy as if it did shine at full intensity for 6 hours a day. As an extreme simplification of this process, consider the rising sun, which shines at half intensity for 1 hour. Then it shines at full intensity for 5 hours, then while setting again, shines at half intensity for 1 hour. These periods of varying solar intensity result in variable power output from the array. If this system employed a 4 kilowatt solar array, half peak intensity results in half power output, or 2 kilowatts, assuming linearity. Consider the first hour of half intensity sun while the sun is still rising. How much energy does this 1 hour period of half power output produce? Energy is power times time. 2 kilowatts times 1 hour yields 2 kilowatt hours of energy. Consider the next period of 5 hours of full intensity sun without a cloud in the sky. How much energy does this 5-hour block of full power output produce? Energy is power times time. 4 kilowatts times 5 hours yields 20 kilowatt hours of energy. Finally, consider the last hour of half intensity sun while the sun is setting. How much energy does this 1 hour period of half power output produce? Energy is power times time. 2 kilowatts times 1 hour yields 2 kilowatt hours of energy. In summation, the 4 kilowatt array exposed to variable intensity sunlight for variable periods of time produces 2 kilowatt hours plus 20 kilowatt hours plus 2 kilowatt hours, or a total of 24 kilowatt hours over the course of a full day. Those with a calculus background will realize that the energy output array is the area under the power curve. 2 kilowatts times 1 hour yields a block with an area of 2 kilowatt hours. 4 kilowatts times 5 hours yields a block with an area of 20 kilowatt hours. 2 kilowatts times 1 hour yields another block with an area of 2 kilowatt hours. 2 kilowatt hours plus 20 kilowatt hours plus 2 kilowatt hours yields 24 kilowatt hours. This is functionally equivalent to an idealized scenario in which the sun shines at full intensity for 6 hours exactly. 4 kilowatts times 6 hours yields a block of energy with an equivalent area of 24 kilowatt hours. While it's easy to visualize using this simplified example, it's not so easy to calculate for actual solar intensity, which does not experience predictable stepwise jumps, but rather increases and decreases gradually and is affected by periods of passing clouds and other nonlinearities. It's for this reason peak sun hours are employed. If you want to think of it this way, the term peak sun hours is a cheat code, which allows an individual a means of quickly estimating average energy output for an array of a given size without having to worry about seasonal shifts, sunrise and set times, climatic conditions, or varying solar intensity. All things being equal, this 4 kilowatt array ultimately produces 24 kilowatt hours of energy each day, whether the sun shines with variable intensity for variable periods of time, or if it pops over the horizon, shines at full intensity for 6 hours, and then immediately goes dark. If you squint your eyes just right, both scenarios, the real variant output in brown and the mathematical equivalent in light orange, yield the same energy output, i.e. area under the power curve, albeit the calculations employing the peak sun hour cheat code is much, much easier. Let's put your understanding of peak sun hours to the test with these two illustrated examples. Consider a 5 kilowatt array installed in an area known to regularly experience 3.5 hours of peak sun each day. Determine how much energy this array will produce each day on average. Second problem. Consider a 4.5 kilowatt array that over the course of a year is known to produce 6,570 kilowatt hours. Determine the peak sun hours this array regularly experiences. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. For the first example, energy is power times time. 5 kilowatts times 3.5 hours yields an average daily energy output of 17.5 kilowatt hours. Too easy. Next example, not as easy. We first need to determine the average daily output of this system. If over the course of a year the system produces 6,570 kilowatt hours, this means the daily output is 6,750 over 365, or 18 kilowatt hours. Time is energy over power. 18 kilowatt hours over 4.5 kilowatts demonstrates the system regularly experiences 4 hours of peak sun. Again, we know the sun shines with varying intensity for varying periods of time, but on average, this system yields an equivalent amount of energy as if the sun shines at full intensity for only 4 hours. All right, last illustrated example before I let you go. Power need to be constant nor linear. Consider the power curve for an industrial wind turbine, which is a graph of power output at different wind speeds. This example will assume the wind turbine has a nameplate rating of 2 megawatts. A power curve is typically defined by 3 points: the cut-in wind speed, the rated speed, and the cut-out speed. The cut-in speed, typically around 4 meters per second, is when the turbine actually starts producing power. Between the cut-in and the rated speed, power increases. At the rated speed, typically around 12 meters per second, the turbine generates its nominal or nameplate value, in this case 2 megawatts. Between the rated speed and the cut-out speed, power flatlines at the nominal value. And finally, at the cut-out speed, typically around 25 meters per second, the turbine shuts down to prevent mechanical damage. Let's say at a wind speed of 10 meters per second, the turbine produces 1.2 megawatts of power. Let's now draw a graph of wind speed for a particular day. Let's say the wind turbine experiences wind speeds of 10 meters per second for 2 hours. Then a 6-hour block of wind speeds 12 meters per second or greater. Then the wind throttles back down to 10 meters per second for another 2 hours, then dies. How much energy does this turbine produce over the course of the day? If you're up to the challenge, by all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Energy is power times time. For the first 2-hour period of 10 meters per second wind, the turbine produces 1.2 megawatts times 2 hours, or 2.4 megawatt hours. For the middle 6-hour period of wind of 12 meters per second or greater, the wind turbine produces 2 megawatts times 6 hours, or 12 megawatt hours of energy. Finally, for the last 2-hour period of 10 meters per second wind, the turbine produces 1.2 megawatts times 2 hours, or 2.4 megawatt hours of energy. In summation, over the course of this single day, the turbine produces 2.4 megawatt hours, plus 12 megawatt hours, plus 2.4 megawatt hours, or 16.8 megawatt hours of energy. If we wanted to, we could express this in units of kilowatt hours as 16,800 kilowatt hours. All right, that's about it for today. In conclusion, this lecture examined energy and power calculations by way of a series of illustrated example problems. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.